Alright guys, we're going to start with what's probably our last vodcast of the semester. We might have some review stuff after this, but this is basically the end of it. A lot of definitions in this stuff, not a lot of math, but you got to move pretty quick with the definitions. So you probably need to pause a lot and write stuff down because I'm going to go through stuff verbally pretty quickly as we roll through this. So we're going to talk first off about different definitions of what an acid is. One of the first guys that really gives us a systematic system for acids is a guy named Arrhenius. And under the Arrhenius system, anything that produces H plus is an acid. So something like hydrochloric acid, a good example, it breaks up in water, okay, and it forms H plus and Cl minus. Sodium hydroxide, on the other hand, is a base because when you put it into water, it breaks up into sodium and hydroxide. So bases produce hydroxides, acids produce H plus. And the important thing here is that things have to be aqueous, okay? Meaning that they have to be dissolved in water for this to be true. So that makes things a little difficult for us because not every time do we have stuff in water. Now, most of the time we do, but not always. And we know now that there are a lot of bases that don't actually produce directly any hydroxide ions. So second system for us for acids and bases is what's called the Brønsted-Lowry system. And this is the one that probably gets used most of the time. It's not as comprehensive, we'll see, as Lewis acids and bases, but it's the one that's sort of easier to understand that we tend to use a lot more. So what is an acid in the Brønsted-Lowry system? Basically, it's something that produces or donates a proton. Now, since a proton basically is an H plus, then that means that all Arrhenius acids become Brønsted-Lowry acids, okay? On the Brønsted-Lowry bases, it has to be a proton acceptor, okay? Now, what does that mean? So, a good example, and probably the most common one of a Brønsted-Lowry base is that of NH3, because what NH3 does is that you can add an H plus to it to turn it into an ammonium ion, okay? There's no hydroxide anywhere in this, but this NH3 does accept this H plus here, and that's what makes it a Brønsted-Lowry base. Okay, so those are the two most common. What's also important here is what's going on in a Brønsted-Lowry reaction. Okay, and so a little bit of terminology here. You've got a reactant that has acids and bases. The proton gets transferred from one thing to another. If it's an acid that only gives up one proton, we say that it's monoprotic. Okay, it produces one hydrogen, in other words. It's polyprotic if it produces more than that. So like an example of this would be HCl. Okay, that's mono because it produces one hydrogen. H2SO4, sulfuric acid, is diprotic, okay, because it produces two. And then we could have something like phosphoric acid, that is what we call triprotic because it produces three hydrogens. Okay? So, the most comprehensive definition of Lewis acids and bases, and probably what scientists sort of like to use the most, or chemists like to use a lot, is that of a Lewis acid and base. Now, we're not going to use it a whole lot because even though it is more comprehensive, it's a little bit harder to understand. It's not as practical just on a day-to-day doing the reaction sort of basis. So, here's what we got. A Lewis acid is something that a molecule or an ion that accepts an electron pair. Now, since these things are tied together, a Lewis base essentially does the opposite, okay? It donates an electron pair, and that's where everything gets formed. So let me show you what this sort of looks like. So we've got an NH3 molecule, okay, ammonia, okay, and it's got this electron pair here. We also have a BF3, okay, a boron trifluoride. And what's going to happen here is that the ammonia is essentially going to donate that pair of electrons to form a bond. And what we're eventually going to get is this slightly more stable molecule. Okay, the BF3, not terribly stable on its own. As you can see, it didn't have enough electrons to satisfy the octet rule. Okay, now what does this mean in terms of Lewis acids and bases? Well, the BF3 accepted an electron pair, so that makes it the Lewis acid. The NH3 donated the electron pair, so that makes it the Lewis base. Now again, we're not going to use those a whole lot, but you kind of need to know what they are. You definitely need to know that ammonia is a good example of not just a Brønsted-Lowry, but also a Lewis base. So this table just summarizes it. You might want to copy this down in your notes just to make sure that you've got a good, solid summary of everything there. So what's really important, another thing that we'll have to learn, and this is particularly true about Brønsted-Lowry, that's what the BL here means, is Brønsted-Lowry acids, is that when they give up stuff or they gain stuff, we have what we call acid-base conjugates. Okay, the conjugate is essentially what's left after the acid does its thing or after the base does its thing in accepting something. Remember, in the Brønsted-Lowry system, acids are going to give up protons, bases are going to gain protons, and so what they turn into on the other side are what's called their conjugates. So just real quickly here, this ammonia we know is a base, okay? And the base, this NH3, it gains a proton, okay? That's what makes it a Lewis base, right? That it gains a proton. And what it becomes on the other side is its conjugate acid, okay? The base turns into the conjugate acid. Now, what's really kind of weird about this is that this, in this case, actually makes water an acid because water is going to give up a hydrogen. The conjugate base here is the hydroxide because after we lose an H+, what's left is OH-. Okay? We'll walk through several of these in class to practice them, but essentially what you need to know is whatever gains a hydrogen, okay, that's the base, and then what it turns into after it gets the hydrogen is the conjugate acid. The acid loses the hydrogen, and it becomes the conjugate base. Alright, so you notice in that last section that water was an acid. Water can actually be either an acid or a base, and there's a special word for that. We call those compounds amphoteric, meaning that basically they can play either side of the equation. They can be the acid or the base. Water's not the only thing. Alcohols, with things with hydroxyl groups, tend to be a good example of that also. Water, though, tends to be the more common one, though. Okay? That's the one that we're going to see the most of. Okay, real quick. Neutralization is what happens when we add acids and bases together. Hydronium ions or H+ ions. So hydronium basically means this, H3O+. And that's just sort of a fancier way of writing H+. These are sort of the same thing. This technically is a hydrogen ion. This is a hydronium ion. Okay? And when they react with hydroxide ions, they're going to form water molecules. So a real classic example of this, and this is the one that we did in the titration lab also, is we take a base, sodium hydroxide, we add it to an acid, hydrochloric acid, and what we get on the other side is NaCl, okay, and H2O. And you might be asking yourself, how does that work? Well, essentially this works out, it's a neutralization reaction, but essentially works out like a double replacement. The sodium goes with the chloride, the OH goes with the H, and so we get sodium chloride, okay, and then HOH, which would be H2O. And generally speaking, this is usually true. If we got a strong acid and a strong base, we get water in some sort of salt. Now, we're using salt here in the generic sense, meaning that it's any ionic compound. Okay, it doesn't have to be NaCl. It could have been anything else as long as it was an ionic compound that came from an acid and a base. That's what generated our salt in that case. All right, almost done here. Water also, we said that it could be either thing, and the reason that water can be either thing is because essentially this is what water does. If I've got two water molecules, okay, two H2Os, then I get an equation set up like this. I've got an H2O plus an H2O, and what we're going to do here is we're going to say that this water is going to give up a hydrogen to this water, and so what we get out of it is an H3O plus, okay, which is hydronium, okay, and hydroxide. Whoops, that's not a plus, that should be a minus on hydroxide, okay? So what does all the terminology here mean? So that means that essentially one of these, and it doesn't really matter which one, but one's an acid, one's a base, okay? This becomes the conjugate acid of the base, and this becomes the conjugate base of the acid. So this turned into this turned into this, and that's what we got. Now, this is important. If we go back to pH that we did in the last unit, this means that we could calculate the pH of water because the concentrations of each of these two things are 1.0 times 10 to the negative 7th if we're in pure water at 25 degrees Celsius. Okay? And if we plug that into the pH formula, we get pH of 7 for neutral water. Okay, now if we take these two things and multiply their concentrations together, remember that brackets mean concentration and molarity, then we get what is called the self-ionization constant of water. We take this, okay, hydronium, or hydrogen, you can just call it hydrogen, that will work out just fine also, okay? Multiply those two things together, and if they're both 1.0 times 10 to the negative 7th, then that gives us a kW value of 1.0 times 10 to the negative 14th. Okay, and we can use that also to figure out, back in the pH section, if we wanted to figure out the OH minus concentration and we were given the H3O plus, we could just plug into this equation instead of having to go through all the pH rigmarole that we did in the last section. Okay, and that's what this is talking about here. At 25 degrees Celsius, kW is 1.0 times 10 negative 14th. This is temperature dependent, so if you're not at room temperature, that value is going to change, but we're pretty much always going to use this value because that's what the temperature in the lab would be on a given day. So if H3O plus and OH minus are equal to each other, then it's a neutral compound, okay, meaning it has a pH of 7. It's acidic if the hydronium ion concentration is greater. In other words, the pH will be lower than 7. Okay? And if the pH is greater than 7, that means that the OH minus concentration is bigger, and so therefore that is a basic or an alkaline solution. Okay? You want to copy this down real quick. Remember that what's important for us is that we, at least in Chem 1, we're just going to do this for strong acids and bases, meaning that they completely break apart, they completely dissociate. If you take Chem 2 or College Chem, we'll talk a little bit about the weaker acids, that they don't completely break apart, and that makes calculating the pH a little bit tougher. Remember that we have diprotic strong acids like sulfuric acid. You can pretty much double the concentration of the ions, and again, that's not strictly speaking true. In Chem 2, we'll talk a little bit more about that, but it's good enough for our purposes now. Same thing if you had a base that had 2 hydroxides on it, like calcium hydroxide. To get the concentration of the hydroxide ions at the beginning, you would just take the concentration of the calcium hydroxide, multiply it by 2, kind of like you do for sulfuric acid. If I had a 1.0 molar H2SO4 concentration, I would double that, and it would have a 2.0 H plus concentration. Okay? So again, if we know Kw, which we do, and we just know one of the ions, either H3O plus or OH minus, then we can figure out what the other one is. We're going to use some indicators in lab pretty soon, and really what you need to know about indicators is that basically they change color at certain pHs, and there's all kinds of different indicators. One that's probably most important to us is phenolphthalein because it has a nice range that kind of changes right in between acid and base. Really it changes around pH 9, but the curve that we're not really going to get that into here, but again in Chem 2 you would, allows that to show us where the change is between acid and base. Okay, we're not going to worry about that equation there, so don't worry about that. This basically is the graph here that shows a titration, okay, and we've done this in class, but you start at a really low pH with the acid, okay, and then as you add more and more base, it goes up, and then finally you hit the point where it sort of jumps up real quick. You see that phenolphthalein is right here, showing the change right there, and then all of a sudden you're at a really basic concentration. This is why in the lab, if you just put in a couple of drops past the endpoint, that it really shoots up quick and it turns to that really deep magenta that we don't really want. So we do all this doing a titration. Remember, the point of a titration is to find an unknown concentration. We're essentially trying to get the acid, the H plus, and the OH minus to equal out. That's called the equivalence point. And why that's useful to us is because we can use the endpoint, which is where the indicator changes color, and then we can calculate the concentration of the standard solution. And these are kind of the steps that you can walk through to do this, but we've done this in the lab, and I think that working through it in the lab will help you out a lot more than any just copying down notes, so that's kind of up to you. Alright, that's probably our last video of the year, guys, at least hopefully maybe a review video. So I hope that you got everything you need there, and I hope you're starting to plan and get ready for the EOC.